So with that, let me jump right into it. Richard, if you go to the next slide. Let me say a few words about the AAVSO, American Association of Variable Star Observers. It's an international organization of us amateurs, and the key there is that we're involved with advancing the science of astronomy, and we do that in a number of ways through professional amateur collaborations. We have databases of long-term observations that the professionals use. We have publications in the Journal of the AAVSO that both our members as well as professionals are involved with. Next bullet there, Richard. Thank you. We also provide various tools, training, support, resources that help our members do science-grade observations. And the key here is that we're involved with doing science, not just taking nice pictures of galaxies and that sort of thing. We have a biannual meeting where we interact both in person and virtually. In fact, one is coming up here in November. Next one, Richard. And finally, we have sections. The AAVSO sections are basically our own little communities of folks to get together where we provide interaction among members on particular topics. We have forums where folks can post questions or comments. So we have very, very involved methods for staying in touch with areas of interest that our members might have. Next slide, Richard. Here are a list of some of the sections. You see there's 12 of them or so, and they range from everything from sort of traditional variable star observing to exoplanets, which we're going to talk about in a minute, to particular aspects of variable stars, solar observing. We recently added a spectroscopy section, and also we have a section primarily involved on instrumentation and essentially taking a look at things like different techniques for using CMOS cameras, CCD cameras, different kinds of filters that are best to use. So we have a range of sections that should fit just about any amateur's interest. But again, the basis for all of this is science and helping to advance the science of astronomy. Next section. And in particular, the exoplanet section. The section provides training and support for conducting exoplanet observations. And again, these can be done with backyard telescopes. We have some observers with as small as 4-inch telescopes doing exoplanet observing. We have a database for storing our observations for long-term archiving, and other resources include courses that we offer online, an observing guide, target lists, alerts, and so on. The last bullet we'll talk a little bit more about this, but the latest space telescope that's been involved with exoplanet discoveries is TESS, the Transiting Exoplanet Survey Satellite. And one of the things that we've done is to work with the TESS science team to develop a qualification process whereby our members now are formal participants with the TESS science team, literally side by side working with the professionals to help confirm exoplanets. Next slide. So I want to say a few words about the big picture, because we kind of get wrapped up sometimes with the sort of nuts and bolts of what we're doing observing wise, and kind of lose sight sometimes of what this is all about. The whole purpose really of NASA's exoplanet discovery missions is ultimately to see if there's some planets outside our solar systems that support life. And we'll talk a minute about what we mean by life. Next. So some related questions that we have to ask in order to determine whether a planet can support life. Is it rocky? Does the planet support liquid water? Does it have an atmosphere? Does the atmosphere contain what we call biosignatures? That is to say, some indication that there are elements in the atmosphere that indicate that life has existed or does exist on the planet. One of the things that has been a little controversial is is a biosignature, that so-called biosignature that we see in the atmosphere, something caused by biological processes or abiologic. That is to say, folks now are seeing that even though we might find things like oxygen and methane in exoplanet atmospheres, it could be that those are caused by things that are due to changes of the physical properties of the planet as opposed to living organisms. So that's a big controversy going on right now with exoplanet scientists. Okay, next slide. And the question is, what forms of life actually might exist? Let me say a few words about something called extremophiles. These are on Earth little creatures. In this case, it's we have here a little tardigrade, or sometimes called a little woolly bear, that's 0.5 millimeter long, that lives and lives off of hydrothermal vents in the bottom of the oceans. And we now have found that they can withstand radiation as well as extreme pressure and temperature. So here we have an example of, quote, life that exists in some very, very extreme circumstances. Next slide. And the question then is, if we look at something like Saturn's moon, Enceladus, which we now believe has an ocean under a crusty mantle. We know that because we see some venting of that. The question is, can something like a tardigrade, next click there, can it exist in something like an ocean on even one of our moons in our solar system? So the whole question of what is life is an interesting question. And with water everywhere now, we know that water exists on exoplanets as well as in the atmosphere of exoplanets. The question is there enough both water as well as other conditions to support life? So the whole point of this is to keep in mind that we're trying to get to the point of discovering whether or not there are sufficient conditions for life. Not that we'll be able to ever see it or experience it or touch it or feel it, but at least coming to some conclusion about whether at least all of the characteristics that would support life, in fact, do exist on an exoplanet. Next slide. So if we take a look at the night sky, click, and we take a look at every star up there, we now know that most stars host one or more planets. Click, and go ahead, Rich. Some of the orientations are such that the planets go around in a circular motion. Next. Some are a little bit more elliptical. Next. And some go across the star in our line of sight. This is the population of exoplanets that we're concerned with here, because these are the ones that we can detect indirectly passing in front of the light of the star. Next. So if we take a look at different kinds of exoplanets, most of the exoplanets that have been discovered so far are what we call hot Jupiters. These are large, close-in planets near their host star. And for that reason, because they are of Jupiter size, we call them hot Jupiters. Next. We have some systems that have multiple planets. TRAPPIST-1 is by far the most interesting one that has 7 planets going around its host star. Next. We have some planets that orbit a star in a multi-star system, where we have 2 stars orbiting each other, where an exoplanet is going around one of those stars. Next. We have some planets that are free-floating, that have been ejected, for example, from their original solar system and are floating free in space. Next. And we have some planets whose orbits are actually opposite from the rotation of their host star. And that's to say they're in this reverse orbital direction, probably because they were captured by their host star and are therefore not part of the original protoplanetary disk that created the star. Next. And finally, we have some stars we've identified that have planets that are disintegrating around them. And we see that through a sort of ring of varying degrees of light as this disintegrating path of material passing in front of the star. Next. So back to what we are involved in as amateurs, and actually what most of the professional community is involved in, which is that particular kind of planet that is transiting across the face of the star. And we use something called the transit method. And if one were to, in fact, take a look at the light of that host star, one would see that sort of bucket-shaped curve that you see at the bottom there, where there's a dip as the planet passes near the limb of the star. It's fully in front of the star, which is at the bottom of the bucket, and then it exits the star. We call that initial dip the ingress, and the last part of it an egress. Next. Now, we can learn a lot from our observations. And again, what you're seeing here actually is an observation I made of an exoplanet from my 11-inch backyard telescope. This is a particular exoplanet called WASP-12. And the key characteristics of the light curve tell us a lot about the planet. That's to say, the duration of the light curve, the depth of the light curve, even the shape of the light curve. Next. The things that we can detect, or that we can ascertain by looking at the light curve would be, for example, the radius or the size of the planet. Next. The size of the orbit. Next. And the inclination of the orbit from our line of sight, simply from the light curve. So we get a lot of information about the planet. Now, we get, as I said, the radius of the planet, but what we don't get is the mass of the planet. And we can't get that with the transit method. There's another method that astronomers use called the radial velocity method that gives us the mass. But once we have the radius and once we have the mass, we can estimate the density. And that gets back to one of our original questions, which is the planet rocky? So if we have both of those parameters, we're able to determine then the density, and therefore, if in fact it's a rocky planet or if it's a gaseous planet. Next. So let me say a few words about TESS, Transit Exoplanet Survey Satellite. Next. And as the name implies, it's doing a survey, an all-sky survey, where it has 4 cameras that dwell on a region of the sky for 27 days goes to the next region. And after 2 years, it's able to completely do a survey of both the northern and southern celestial sphere. TESS is now in its 4th year, so it's actually done this twice. So it has actually now surveyed the entire celestial sphere, with the exception of a small swatch in the middle. It's been able to do that twice now, which means it's been able to revisit some of the exoplanets that it originally had observed. Next. So the TESS mission itself was launched 4 years ago, as I said, and its primary mission was to look at nearby bright stars. By nearby, we mean within 30 to 300 light years. Next. And the whole purpose, or one of the main purposes of TESS, was to find candidates for the James Webb Space Telescope, which, as you know, was just launched just recently, is now in science operation. And the reason for that is because one of the main missions of JWST is to look in the infrared or near infrared at a planet as it transits a host star, and to look at signatures in the near infrared that give an indication of what are the elements in that atmosphere. So that gets back to one of the questions we had earlier about biosignatures. So JWST will help characterize the atmospheres of the planets that TESS has identified. So far, TESS has found 5,800 candidates and has confirmed 231 of them. We'll see in a minute that the whole confirmation process from being a candidate to confirm is a very rigorous process. And this is where amateur astronomers play a big role. Next. And the reason for that is because we need to do ground-based observing. Now, why do we need to do ground-based observing? We have this wonderful telescope up in space. It's above our atmosphere. But the problem is that in doing a all-sky survey, TESS has very large pixels. And because of that, as we'll see in an example in a minute, light from multiple stars get blended together in a TESS image. So a dip in light that's caused by a exoplanet transit might be actually a false positive. What might appear to be an exoplanet transit might actually be a false positive. And what we need then are ground-based observers to follow up and to sort out what's a true exoplanet transit from a false positive. Next. The process for confirming an exoplanet, as I said, is very rigorous. It starts at the top with ground-based observing. Once a candidate passes through that filter, if you will, there's some high-resolution imaging that's done, spectroscopy is done, radio velocity is done to measure the planet's mass. So it's the first part of that, next, that amateur astronomers are involved in. So we, on the ground, are observing the candidates that TESS has identified to help determine whether, in fact, there are false positives or not. Next. Now, let me kind of dwell on that a little bit more to give you a feel for some actual examples here. This is an image I took of a candidate exoplanet. And again, this is a ground-based CCD image. Next. If we zoom in to those two stars in the middle, next, you'll see that the pixel size of, for example, my camera is what you see there. It's about 1 arcsecond per pixel. However, if you were to take a look at a pixel that TESS has of those same stars, next, you'll see that its pixel, and again, we're talking about a single pixel here, is 21 arcseconds. So the test pixel is so large that for the most part is covering multiple stars. Next. So the light from those stars get blended together. So light in a single test pixel, we're not able to discern whether any changes in light are coming from one star or the other. Next. And the problem gets even worse. If we zoom out a little bit and see that that test pixel is in the middle covering two stars, those of you who are familiar with photometry, where we put a so-called aperture around an area and then look at the light in that aperture, the test aperture even consists of multiple pixels. Next. And so the test aperture, go ahead, click again. The test aperture even covers more pixels. So the problem gets even worse. So the bottom line is with the large pixel size that TESS has and the large photometric aperture, there's a lot of blending of light going on. And so if there's a dip in light of that area, TESS in many cases is not resolvable enough to determine where and if that light is being caused by an exoplanet. Next. Now, some of the conditions that cause false positives that we use our ground-based observing to distinguish have to do with a number of cases. One is where we have a target star on the left, and next to it is a nearby eclipsing binary. That's to say, two stars that are eclipsing each other. From a ground-based point of view, we're able to separate those out to see where any dip in light is occurring. In this case, it's occurring on the eclipsing binary. However, TESS will see both of these objects together and won't be able to distinguish where the dip in light is coming from. So this is one case. Next. The second case is where the nearby eclipsing binary is so close to the target star that even our amateur astronomer scopes cannot resolve the difference. What we then have to do is to rely on a little bit larger professional telescopes. But for the most part, we're able to detect the very first case here. And that, in fact, is one of the dominant cases for false positives. Next. Another example is where there is a star that is orbiting a nearby eclipsing binary. And again, we still have that same problem of blending. Next. We have the case of the host star is an eclipsing binary and it's being blended with a neighbor. Next. And the case of, we just have a regular old eclipsing binary, but the secondary star is so small that when it's going in front of its host star, it's mimicking an exoplanet. Next. And finally, a case where the secondary star is grazing the primary star and it even further looks like an exoplanet. So all of these cases are ones that we amateur astronomers are looking at on our ground-based telescopes and providing data to NASA to help make the distinction about whether it's a false positive or a true exoplanet. Next. Now, I mentioned earlier that the light curve itself is very valuable in helping us to determine not only the parameters about exoplanets, but also whether there's false positives. If we see, for example, a bucket-shaped curve, more than likely that's an exoplanet. If we see a very sharp V-shaped curve, more than likely it's an eclipsing binary. Next. If we see alternating or odd-even V-shaped curves, then again, more likely that's a eclipsing binary because we have a large and a small star eclipsing each other. So we see these different in depths. Next. if we see difference in chromaticity, that's to say, if we use a blue filter, we get a certain depth, and if we use a red filter, we get a different depth, more than likely this is an eclipsing binary, because an exoplanet will cause a dip in light, but not a change relative to differences in color. So all of these things are ones that we amateur astronomers can do fairly easily to help make that distinction. Next. And finally, just the depth itself. If the depth is over a certain amount, which indicates that the radius is more than 2.5 times the radius of Jupiter, then more than likely it's not an exoplanet. It's probably a eclipsing binary. Next. So to give you an example of an actual observation, next. This was one observation done by some colleagues of mine up in upstate New York, again, amateur astronomers. And they did this in a red filter. Next. On a different epoch, about 11 eclipses later, I did an observation in a blue filter. Next. But if we combine the two, we see this chromaticity difference. And this nails, in fact, that this, in fact, was an eclipsing binary. Next. Now, to give you a quantitative idea about this, the ability for some of these false positives to look like an exoplanet, let's assume we have a target star. Let's take the case of it having a nearby eclipsing binary, where on a ground-based observer, we would see a very V-shaped curve for that nearby eclipsing binary. Next. And let's apply some numbers here. So if we have an 11 magnitude target star and a nearby eclipsing binary that together have about a 13.5 magnitude brightness, and let's say the depth is 100 parts per thousand of that eclipsing binary. So these would be something that we're seeing here on our ground-based observing. Next. If TESS were to look at this, next, what it would see would be on the right. It would see a target with a 10 parts per thousand depth, which looks very much like an exoplanet. So what TESS is seeing on the right is different from what we on Earth are able to discern, which is the separation between a target and eclipsing binary with a very sharp V-shaped curve. Okay, next, Richard. Now, one of the issues is that if we're looking at a target like we are here, because of the large aperture, photometric aperture that TESS has, we have to look at a number of different targets, potential stars around the target, to see if they are, in fact, eclipsing binaries that might be producing a false positive. So here's an example where normally it would be the case we'd have to go and look at each one of these individual stars in green to see if, in fact, it's an eclipsing binary. A very cumbersome process. So what we in the AAVSO did was to develop a program to do this automatically for the TESS science team. Next. And we're able to do that. We added a feature to a data reduction software called AstroImage to be able to actually do that analysis on the order of a few minutes, whereas it was taking hours of manpower to do. So one contribution that we made to the TESS science team was some software to streamline their ability to test all of these different cases in the field of view of a TESS aperture to check whether there were, for example, any eclipsing binaries taking place. Next. And this feature was something that we added to to this software package. And now it's in fact probably one of the most used features that the professionals use to help discern false positives. Next. So some of the contributions, just to summarize, that we've made to, in particular, the test mission is, if you were to count the number of submissions that have occurred as far as follow-up ground-based submissions, the majority of them have been from amateur astronomers. As I said, we've developed some analysis tools. We actually developed the submission guidelines for the entire test team. We've helped with the analysis even of observations from remote professional observatories, such as LCO. Next. One of the things that I kind of alluded to earlier that we make available to our members, if they're interested in exoplanet observing, is courses, both online and live, that we have. I just conducted, for example, a 6-week online course on sort of advanced exoplanet observing. There's a practical guide to exoplanet observing that is on my website. I have a reference to it later. This guide is oriented toward folks like me who started out doing imaging of, regular planets or galaxies or nebula. So somebody with some imaging experience who want to get into exoplanet observing, it sort of walks you through the best practices. And also the second half of it is a tutorial on this data reduction program I showed earlier called AstroImage-J. Any of you who are interested in getting into exoplanet observing, I suggest that you go to my website, take a look at some of the resources that are there. Go to our section page at the AAVSO. We have a qualification program for members to participate in the test science follow-up program. Right now, we have 26 members that are qualified, that are participating in that program. So I would urge any of you who are interested in getting into exoplanet observing, we have plenty of resources to help you get involved. Next. So where's NASA going with their future exoplanet missions? Next. Well, the one you've heard about so much in the news lately is James Webb. And as it's just starting its science mission, it is now going to be taking observations in the near infrared. In fact, if you saw one of the original, I think 5 or so objects that were rolled out a couple weeks ago, one of them was an exoplanet curve showing in the near infrared the various atmospheric components of a particular exoplanet. And this is one of the key things that Webb is going to be doing, is characterizing exoplanets. So if you remember those series of questions that I outlined earlier, is the planet rocky? One of the key questions is, are there biosignatures in the atmosphere? And that's where we're at now in our discovery process with exoplanets. Next. Now, coming up, hopefully in the next decade, is the Roman Space Telescope. And for the first time, we'll be able now to start directly imaging exoplanet atmospheres. So the Roman Space Telescope will take us really to the next step beyond even what Webb is able to do. Next. So to summarize, next, I hope I've sort of convinced you that amateur astronomers have already proven our value. The test mission is an example where we participated with professionals to really help them, especially in the planet confirmation process. Next. One of the things that is true in the test mission, that anybody who's involved in it If your data is used in a discovery paper, you have the opportunity to be a co-author of that paper. Many of us now are co-authors, for example, on many papers. I probably am co-author on probably 24 papers already. So it provides for some very interesting contribution you can make, not only from an observational point of view, but also literally to be part of the scientific paper. Next. And again, this whole process of what we are doing as amateurs in exoplanet discovery has its roots in the experience we've gained in astroimaging. So any of you involved in deep sky imaging or planetary imaging, your experience is directly relatable to some of the principles in doing exoplanet observing. Next. And finally, as I mentioned, if you are interested, I encourage you to take a look at what AAVSO offers in terms of helping you bring you up to speed on the best practices in exoplanet observing. Next. Here's some contact information for myself. Feel free to email me. If you just go to astrodennis.com, you'll see a example of some exoplanet images that have been taken, and the practical guide I mentioned earlier actually uses those images as an example. So you can literally download the images, and as you're walking through the guide, you can see how those images go through the whole process of calibration all the way through to detection of an exoplanet. Let me stop there. I have one more slide, but let me hold that to the end and just open it up for any questions.
I have one, Dennis. You mentioned, the equipment. What would be kind of like a basic rig? Like what kind of, do you need to have auto guiders?
Yeah.
How well does your mount have to track since you're doing these time series photometries? Any kind of filters? What would you need?
Good question. Okay, let me start with the mount, which is generally one of the most important elements of any of this. Yeah, the mount should be, a pretty decent mount. I have a Los Mondi P11. As far as tracking, auto guiding, definitely. And the reason for that is because when you imagine that if there's any image shift occurring, because of the precision that we're trying to get as let's say the host star that we're tracking, its light, if it moves across the field of view because the tracking isn't quite up to snuff, it's going to land on maybe a dust mote, or it could land on pixels that, dark pixels or pixels of different sensitivity. So ideally, we'd like to keep the image as stable as possible on the field of view. So definitely guiding, in particular, off-axis guiding. I actually use on-axis guiding, which is really guiding on the target star itself. And it's through a little split mirror that actually has the target star, not some star off the field of view, but the target star being used as the guide star. So definitely guiding would be important. Now, as far as the telescope itself, ideally, I would say 8-inch, preferably 11-inch or larger. I mentioned earlier, we do have some small scopes, these EV scopes that are 4 inches that are run for roughly $4,000. Some folks are now using those for exoplanet observing. The difference is the depth you're able to detect. So with these small scopes, 4-inch scopes, you're able to detect maybe a 1% dip in light, which would be for hot Jupiters. But to detect something on the order of, let's say, mini Neptunes, for example, one would need a larger scope and, pretty decent scene conditions. I mean, I'm here in Annapolis, Maryland, in the suburbs, some light pollution to the north. And, I can do pretty good exoplanet observing from here, my 11-inch scope. As far as filters, ideally standard filters, but if it came down to it, maybe even a V filter. There's such a thing as a so-called exoplanet filter from Astrodyne. But even a clear filter, if it's a matter of just detecting whether it's a V-shaped curve or a bucket curve, even just a clear filter. As far as the camera, we have many folks now using CMOS cameras, and I have a Starlight Express camera I've had for years now, which is a CCD camera that performs quite well. So one does not need a full frame, back illuminated camera to do some decent imaging. I think that, any other questions on that, Richard? Does that cover most of it?
No, that covers it pretty well. And I think anyone who's doing, as you mentioned, any kind of long duration, like DSO astrophotography, has the mount and guiding to do that.
Exactly. Yeah. Yeah. Even now, folks who are doing deep sky imaging who have, for example, RGB filters, we have some folks who are using even those, those filters for the exoplanet observing. So
yeah, that's what I feel too. That's why I asked about the filters, because they probably don't have a photometric filter to do the chromas that you were talking about, but you can detect the dips and in the shade. Even with a clear filter would be fine for just detecting whether there's a transit, but then getting a little bit more involved doing the chromaticity, ideally, a Johnson Cousins or SDSS photometric filter. But yeah, the transition from deep sky imaging or planetary imaging to exoplanet imaging is a lot of the same principles. I mean, doing your flats, darks, biases, calibration, all of that is the same. Any other questions?
Yeah, there's a couple here.
Question: you use prime focus or you use eyepiece projection?
Can you hear that, Dennis?
No. Could you repeat the question? I'm sorry.
I wanted to know if he uses prime focus for imaging or eyepiece projection.
Do you use prime focus or eyepiece projection?
Prime focus. In other words, the camera. Let me just make sure I got the terms right. The camera on the end of the telescope, not projected onto something. If that was the question.
Yes.
Yes, that was the question.
Yeah.
Then there's another one.
Dennis, thank you for a great presentation and a great write-up too on your, can you hear me okay?
Yeah, go ahead. Yeah.
Actually, I got 5 questions, if that's okay. I was intrigued about the tilt on the exoplanets. Have you found them to be equally dispersed, or is there a bias with the expanding, global universe type stuff? Were they equally dispersed in the tilt angle, or is there a bias?
You're talking about the inclination? We say tilt.
Yeah.
No, they're equally distributed. I mean, there's some that are dead on, straight line of sight. There are others that are so much tilted that they're kind of grazing the planet. I mean, when you think about it, it's the observations that we see are kind of biased towards more that are on our line of sight because they're easier to detect. But when you think about it, the orbits are just, can be any direction probably. I don't know what the statistics are, but, I don't think there's any particular orientation, except we just happen to be biased to ones that are, more straight on our line of sight.
Gotcha. Next question. In terms of the minor planet, I've done some minor planet work, and the saturation with the full sky surveys are kind of knocking out a lot of amateurs out of that field. Is the all sky surveys Is there any work to automate that, to track, not knowing the timeline for exoplanet work on the persistency that you're actually tracking, the dip? But are the all-sky surveys able to do that, and therefore kind of taking part of the chunk out of the amateur astronomer contributions?
Are you talking about ground-based all-sky surveys?
Yes, sir.
There was actually a ground-based all-sky survey called KELT that was done, but it didn't have the resolution that even our amateur astronomer scope have. So I don't know if that answers your question, but
I might say a little about that too, because if you look at all of the surveys, like Assassin is a big all-sky survey, they survey every patch of the sky once per night. That's their goal. And they get pretty close. Sometimes it'll be 2 a night. So when you're looking for these transits, you're really taking photometry of the same area over and over for a longer period of time. And so there's no survey out there that I know of currently that's really doing that. They're sweeping the sky and moving along, where you're picking out, if you're doing this, specific targets and sitting on it on pretty much all night to get that dip. So you're doing 2 different things. You're right that the surveys are pushing out a lot of observations in a lot of other areas, especially if you look at something like I do with longer term LPVs. That's taken a lot of that over, but I don't think exoplanets is going to be anytime soon, or even eclipsing binary work. They're very similar.
Your goal is amateur imaging. You're really going for a long, continuous, constant imaging overnight.
yeah, in fact, typically 6 hours.
Wow. Okay. Thank you.
Yeah.
Awesome. In terms of the scope, Schmidt Cassegrain, RC, corrected Doppler, anything? Is there any bias or preference in that?
No, I think all of them have been used. I think aperture size is probably the key, though. But yeah.
And then, what's your recommended arc seconds per pixel for imaging?
Well, it's also a function of your seeing. I have 1 arc second per pixel is the image scale that I use here. Yeah, and that works fine. So I think it, again, if you can get better, depends on your seeing conditions.
And I had interface with Arnie Hendon several years ago. Is he still with the program? He was working.
Oh yeah, Arnie's still around. Oh yeah.
He had a CCD book that I did a little contribution for him. Did that ever get published, or?
There's a guide, CCD guide to photometry that the AAVSO has as one of its resources that I'm sure Arnie was a big part of.
They also sell his he did a school. It's like it's a C. I think there's CDs. They may have digitized it at some point, but it's like hours and hours of training that I think you can purchase it.
Yeah, on transformations and other things. Yeah.
Thank you, Dennis. That was great.
Sure.
Question in the chat.
Yeah, Bruce has got a question in the chat. I saw.
Hi, can you hear me okay?
Yeah.
Yeah, Mr. Conti, thanks for a fantastic presentation, and thanks for your time tonight.
Sure.
So I don't have a big expensive astrophotography setup, but if I'm ever fortunate enough to retire in my lifetime, I've had my eye on these unistellar EV scopes, which are kind of the next generation of imaging telescopes, and they advertise a worldwide network of anybody that happens to drop $6,000 on the scope can network to find exoplanets. And I'm staring at this web page that they presented at a NASA test conference and so forth. So what's your opinion of the unistellar EV scope and its contributions to this? Is that
right? So if you recall, I mentioned earlier that we have folks who using a 4-inch scope. That's an EV scope.
okay?
But let me just caution you with this. As I said, those scopes, those 4-inch scopes, they are fixed exposure time of 4 seconds. It's like 3.9 seconds, and you got to live with that, which means that you've got to take, in some cases, 4,000 images over a period of time to do an across a 6-hour period, for example, or whatever 4 seconds comes to over 6 hours. Which means that the volume of images is huge. Now, the way that EV scopes operate, or Unistellar, I should say, operate, is your data is uploaded to them. And the observer does not do the analysis, except more recently. Let me qualify that. What has happened previously is that data is sent to SETI, and folks there have been doing the analysis. More recently, in fact, in the training program I just did, there were a couple of individuals who had EV scopes that were learning how to do exoplanet analysis. But the process is still getting worked out of how you would get images that you took after they're uploaded to Unistellar. Those then have to be downloaded back to you if you're going to be doing the analysis. And they're working out right now how to streamline that. But that's right now one of the complications is getting your own images back to you, because they're automatically uploaded to the Unistellar network. So I don't know if that makes sense, but basically there's not a lot of exoplanet observing going on right now. There's a few folks who are doing it. There's probably more that are going to start doing it, but there's a little process flow that has to get ironed out a little bit more efficiently.
I see. Okay, thanks very much. Yeah, at my job, I analyze my own data. So
Yeah. And as I said, those small scopes are good for maybe 1% transits, which are like the hot Jupiter size exoplanets, but tougher for some of the smaller exoplanets.
sure. Thank you very much.
Sure.
Dennis, another question. What is the typical cycle time then? Is it like planet Earth? It's going to take a year, and therefore to get confirmation, you're going to have 2 or 3 years to create a light curve? What is there a typical life cycle or cycle?
Yeah, no, actually a lot quicker. First of all, TESS will identify a candidate if it has seen 2 eclipses. And now, because we're talking about planets that are close in to their star, in one of those 27 days that TESS is dwelling on a particular part of the sky, it would have to see 2 eclipses, which means 13 days at most of a period. Once those eclipses have been seen, if they have been seen, then it goes into the TESS pipeline, which is pretty quick. The TESS science team pops it out maybe in, I'm going to say, a few weeks as a candidate. Then it starts going through that pipeline confirmation process. That could go anywhere from, 4 months to a year, depending upon what resources are available. But in some cases, maybe 6 months. So it's really the longest period of time is just going through that rigorous process. And that's where the time is. And then, of course, writing up a discovery paper, that probably even takes longer. But
So that applies to our kind of solar system. You're talking about a Mercury, Venus type, or even sub Mercury, Venus, even closer in terms of the period around the sun.
oh yeah, much closer than even Venus. Yeah, we're talking days of orbit around the host star.
So is that the precursor then? In other words, they pick something up, therefore they now there's a planet surrounding it, and then you assume there are other in the Goldilocks zone and all that other stuff, or are there multiple passes?
Yeah, well, so when the first planet is identified, usually it's the one that's closest in, and depending upon the host star, let me give you an example. What TESS is focused on mostly are M stars, which are cooler stars, which means that the planet can be closer in, and therefore in the, as you said, the Goldilocks zone or the habitable zone. So one of the nice things about the TESS survey is picking up planets that have a higher chance of being in the habitable zone because they're around cool stars and therefore the planets can be closer in, which means we can more easily detect them via transit method. So yeah, so typically after the first planet is identified, then folks kind of think there's probably a higher probability there's other planets out there. So they're looking for the existence of other planets, either through transits, other transits that they periodically see, or through what are called transit timing variations. If they see that the time of the orbit of a particular exoplanet slowly changes, that says it's probably being perturbed by some other planet. And so that's a hint that maybe there's a second planet. So yeah, typically the closest in planet is discovered first, and then later the planets further out are discovered.
Have any of the amateurs picked up a second light curve? In other words, 2 planetary hits?
I'm sorry, say again?
Have any of the amateurs in the team picked up any like 2 light curve hits, so 2 planets orbiting? In other words, oh my God, there's one at one period, another one at a different period?
Not that I'm aware of. Most because the second planet would be further out, which means its depth would be probably smaller, which means it would be harder for an amateur to detect. So yeah, I'm not aware of any. Typically, us amateurs have detected what I'll call, quote, the primary planet, that is to say the initial discovery planet.
Thank you.
Sure. Any other questions? Okay, well, I want to thank Richard for helping me with this fallback presentation here, being able to do it locally there. Thank you much.
Happy to be useful.
Thank you. Okay. Thank you.
Thank you,
Thanks,
Dennis.
Dennis.